You know, every single day we send texts, emails, and photos zipping across the globe, and they get there in what feels like an instant. It seems like magic, right? But it's actually an incredible, high-speed journey. Today, we're going to follow one of those messages and uncover all the secrets of its amazing voyage.
But have you ever really stopped to think about how that works? I mean, you hit send on a text, and poof, it just shows up on your friend's screen, maybe halfway around the world. How does that actually happen? What's the path it takes? And what kind of dangers does it have to overcome along the way?
Okay, now this might look a little complicated, but I want you to just think of it as a roadmap. This is the entire journey of our digital message, laid out from start to finish. It shows every single step, every transformation, from the second you type it to the moment it gets read. We're going to trace this route together, and I promise, by the end, it'll all make perfect sense.
So, let's kick things off at the very beginning. Our message is basically the hero of this story, and it's about to go on this epic quest through a wild world of digital networks. But before it can even leave your phone, it has to get ready for the trip. This is where it all starts.
The very first hurdle is a language barrier. See, our computers and phones, well, they don't speak English. They speak in numbers. Specifically, they only speak in ones and zeros. So the first thing our message has to do is find a translator.
To make this journey super easy to follow, we're going to track one single, simple word from start to finish. And that word is think. Just 5 little letters, but they're going to take us through this entire incredible process.
In this table right here, this is the dictionary. It's called the ASCII table, and it's basically a universal translator for computers. As you can see, it gives every letter, number, and symbol its own unique code. See how the capital letter T has its own specific string of ones and zeros? This is what makes sure that a T you send from your phone is understood as a T by any other computer on the planet.
So, after a quick trip to that ASCII dictionary, our word think is totally transformed. It's not letters anymore. Now it's a stream of bits, a sequence of ones and zeros. Our message is finally speaking the language of machines. It's ready for the next leg of its journey.
Now that our message is in binary, we could, technically, just send it as is. But here's the thing. In the digital world, size really matters. The bigger the message, the longer it takes to travel, and the more space it takes up on the network. So what's the solution? Well, our message needs to pack light.
Now, this process of making the message smaller has a technical name. It's called source coding, but you definitely know it by its more common name, data compression. Just think of it like being an expert packer. Trying to fit everything you need for a week-long trip into the smallest suitcase possible so your journey is faster and way more efficient.
What's really cool about this is that there are 2 main ways to pack our data. First, there's lossless compression. That's kind of like vacuum sealing your clothes. Everything comes out at the other end looking exactly as it went in. It's perfect for things like text or computer code. Then you have lossy compression, which is a bit more aggressive. It cleverly throws away tiny little details you probably wouldn't even notice just to make the file much smaller.
And this is a fantastic example of what I mean. Check out this sunflower. The original image on the left is 738 kilobytes, but with lossy compression, we get it all the way down to just 147 kilobytes. That's less than a quarter of the original size. And honestly, the quality still looks amazing. This is the magic that makes streaming a 4K movie even possible without it buffering every 5 seconds.
Okay, so our message is now lean and efficient. But being fast isn't everything. It's about to travel through public networks, which you can think of as the digital version of a crowded city street. Anyone could be listening in. So our message needs a way to stay secret. It needs a cloak of invisibility.
And that cloak is called encryption. Looking at this diagram, the idea is actually pretty simple. You take your normal readable message, which we call plaintext, and you use a secret key to scramble it up into something unreadable, which we call ciphertext. The only way to unscramble it is if you have the correct key. This is exactly what's going on when you see that little padlock icon up in your browser's address bar.
Here's a really simple, classic example of how this works, kind of like a secret decoder ring. This is a Caesar cipher. The key is just shift every letter forward by 3 places. So as you can see, the N in now becomes a Q, the O becomes an R, and the W becomes a Z. To anyone who doesn't know the shift by 3 rule, the ciphertext QRZ is just complete gibberish. Of course, modern encryption is way more complex than this, but the basic idea is exactly the same.
So our message is small and it's secret. You'd think we're ready to go, right? Well, not quite. There's one last major danger out there on the journey.
Noise. And I don't mean sound. In the digital world, noise is any kind of electronic interference that can accidentally flip a 1 to a 0 or a 0 to a 1, totally corrupting our message. It's the reason why your video call might get all pixelated on a bad connection. So our message needs one last thing, a suit of armor.
This suit of armor is called channel coding. What we do is strategically add a few extra redundant bits of information to the message. Now, these extra bits don't add any new meaning, but they act like a checksum. They give the receiver a way to double-check if the message got damaged along the way, and a lot of the time, even fix the errors automatically.
So here's a super simple example of how that works. It's called a parity bit. Let's say we make a simple rule. Every chunk of data we send must always have an even number of ones. Okay, look at that top row. The data is 1010. It already has 2 ones, which is an even number, so we just add a 0 as the extra parity bit. But now look at the second row. The data is 1101. That has 3 ones, an odd number. So to make the total even, we add a 1. Now if that message gets to the other end and the receiver counts an odd number of ones, it knows instantly that an error happened, and it can ask for the data to be sent again. Pretty clever, right?
And with that, our little message, think, has finally done it. It was translated into binary, it was compressed to be smaller, it was encrypted for secrecy, and it was armored up for protection. It has survived the entire journey and has finally arrived at its destination.
So now that it's arrived, everything that we just did to prepare the message for its journey, well, it all just happens in reverse. Take a look at the bottom half of our roadmap. The receiver takes off the armor, that's the channel decoding, then it uses the secret key to decrypt the message, it decompresses it back to its original size, and finally, it uses that same ASCII table to translate the binary code back into the 5 letters we started with, THINK. The journey is complete.
And here's the most mind-blowing part. This entire complex journey happens thousands, even millions of times every single second all around us. It's the invisible backbone of our entire modern world. It really makes you wonder, right? With our demand for data growing every single day, what's next? What new innovations in things like quantum communication or AI-powered networks will be the next frontier for sending our information even faster, safer, and more reliably?